This animation is intended to illustrate the steps required for creating a Norton equivalent circuit. According to Norton's theorem, any two-terminal circuit made up of fixed-value resistances and of voltage and current sources can be replaced by a single current source in parallel with a single resistance, which will produce the same effects at the terminals. There are 4 basic steps involved in creating the Norton equivalent circuit. Step 1 of the process involves identifying the portion of the network for which the Norton equivalent circuit is to be determined. We then label the two terminals as points A and B and remove the portion of the circuit that is not being included in the simplification. In step 2 of the process, we remove and short circuit any voltage sources in the network and remove and open circuit any current sources. We then calculate the Norton equivalent resistance as it appears between the open terminals, previously labeled as points A and B in step 1. For step 3, we return the sources in the network to their original state and position. We then short circuit terminals A and B and calculate the Norton equivalent current, IN, at that point in the circuit. To complete the process, we draw the equivalent circuit using the values we have calculated for the Norton equivalent resistance and current. For this example, we will use the simple resistive network shown here. This network contains a single voltage source and 4 resistors. We have assigned values to each component in the network. To determine the Norton equivalent circuit, we follow the steps illustrated previously. We begin with step 1. Identify the portion of the network for which the Norton equivalent circuit is to be determined. We then label the terminals connecting this portion to the remaining part of the circuit as points A and B. To complete the first step in the process, we remove the portion of the network that is not being included in the simplification. The next step in the process is to calculate the Norton equivalent resistance as it appears between terminals A and B. We begin step 2 by removing and short-circuiting the single voltage source that is present in the network. We are now ready to calculate the Norton equivalent resistance, Rn, appearing between points A and B in the circuit. To do this, we must reduce this resistive network down to a single equivalent resistance. To begin the reduction, we calculate the equivalent resistance of R1 in parallel with R2 by using the product over sum rule. Next, we sum the series resistances R3 and REQ12. To complete the calculation of Rn, combine the parallel resistances R4 and REQ123. The Norton equivalent resistance, Rn, for this sample network is equal to 75 ohms. Once the Norton equivalent resistance has been determined, we move on to step 3 and calculate the Norton equivalent current, In. First, return all sources in the portion of the network for which the Norton equivalent circuit is being determined to their original state and position. Next, we create a short circuit between points A and B in the circuit. With the circuit in this condition, calculate the Norton equivalent current, In, which flows through points A and B in the circuit. It is important to note that there is a short circuit around resistor R4, which effectively removes it from the circuit. There will be no current flowing through this resistor. In terms of calculating the Norton equivalent current, resistor R4 can be removed, as it has no part in determining the current flowing between points A and B. We now calculate the remaining total resistance in the circuit and use Ohm's law to get the current flowing from the source. With the circuit in this configuration, we can see that R2 is in parallel with R3, and both of these are in series with R1. We now use the value of E and the total remaining resistance to calculate the current flowing from the source. Once we have determined the total current flowing in the circuit, we use the current divider rule to calculate the Norton equivalent current. This current flows through R3 as well as through points A and B. The Norton equivalent current, IN, for this sample network is equal to 80 milliamps. We complete the conversion by drawing the equivalent circuit using the calculated value for Norton current and Norton resistance. The behavior of the original network and the Norton equivalent circuit are identical with respect to points A and B. This type of circuit reduction is extremely useful when attempting to determine the effects of varying load conditions on load voltage and current.